In this step we will copy the surface we made in the last tutorial and reuse it for this part. Firstly, switch to the nose gear rim part window. Select the multiple extract surface that we created in the last tutorial, and then right-click and choose Copy from the menu. Now return to the nose gear tire part window. Right-click on the 3D shape and choose Paste Special. In the pop-up window, select it as Result with Link option and press OK. Using this method creates a link between the surfaces, therefore if the geometry of the rim changes, it will also change the surface automatically as well. To help us in the next step, we will split the surface in half and only use the upper part. In the Transform toolbar, click the Split command. Select the copied surface as the element to cut, and the XY plane as the cutting element. Make sure the upper half remains. If needed, the side to be kept can be changed using the Swap Sides button next to the cutting element. Click OK to cut the surface. In this step we will revolve a sketch around an axis, similar to a shaft, but this time the result will be a surface. Create a sketch on the YZ plane. We will start with the axis line. Draw it in line with the horizontal axis to constrain it. Next we will create the yellow line shown in the sketch, which is an intersection with the surface. To create it, click the surface and in the contextual menu choose the Intersect 3D Elements button. Change the line to a construction element. Now use the Profile tool to create the last part of the sketch. We will intentionally draw it skew so that we do not get the vertical constraints. Remember to click and drag to be able to create an arc. To end the profile, press the Escape key on your keyboard. As you can see, we are missing the second tangent constraint, so we will add one using the contextual menus. Next, add the coincidence constraints between the vertical lines and the flange surfaces. We can use the Normal View command to realign the sketch. Add the length constraint with the radius diameter option. For all values in CATIA, if we add the unit to the end, they will be converted. Since tires are typically given in inches, we can use 11 inches and CATIA will convert it to 279.4 millimeters. As can be seen in the image, the radius constraint is given as reference. We can use the right-click menu to change a constraint to a reference value when creating it. Finally, we will constrain the axis length to 150 millimeters and then make it symmetric. This is done by multi-selecting the two end points and then the symmetry line, which is the vertical axis. This gives us the fast symmetry option in the contextual pop-up. The sketch is now fully constrained and we can exit it. Now we will make the surface. In the Surface toolbar, click the Revolve command found underneath the Extrude command. Set the first limit angle to 0 degrees and the second limit angle to 90 degrees. Click OK to create the surface. We will now create an offset surface from the Revolve to help create the tread of the tire. In the Transform toolbar, click the Offset command. Use the Revolve surface for the surface. Set the offset to 2 millimeters. Click the Preview button to see if the surface is created on the inside, if not, click arrow to change the direction. Click OK to create the surface. We will now use the surfaces to start creating the tire geometry, so we will need to use the Part Design app. Use the compass to switch to the Part Design app. Make the part body the in-work object by right-clicking it and choosing Define in-work object. Notice that it is now underlined and any features will be added to it. In the Essentials toolbar, click the Thick Surface command. Use the Revolve surface as the object to offset. Set the first offset to 8 millimeters. and the second offset to 0 mm. Click Preview to see that the geometry is made on the inside of the surface. If not, change the direction by clicking the arrow in the geometry or the reverse direction button, so that the geometry is made on the inside of the surface. Click OK to create the geometry. We will now split the geometry, so that we can more efficiently create the tread of the tire. In the Transform toolbar, click the Split command. Next, select the ZX plane as the splitting element. Ensure that the arrow is pointing in the positive Y direction. Click OK to cut the geometry. In this step we will add a second body, which we will use to remove material from the part body using a Boolean operation in the upcoming steps. In the Structure toolbar, select the Body command. Right-click on the new body and select Properties. Under the Feature Properties tab, rename the body to Remove. And under the Graphic tab, change the color to match the displayed model. Click OK and then make sure it is the in-work object. Create a sketch on the ZX plane. First we will create a rectangle starting from the origin point. Draw a line on one of the diagonals and make it a construction element. Constrain the length of one side to 170 mm. Then constrain the angle to 45 degrees to create a square. Exit the sketch and use it to create a pad. Use a first limit dimension of 3 mm and use the symmetry option to make the pad the same length on both sides. Click OK to create the pad. In this step we will pattern the previous pad. Select the pad 1 in the model tree so that it is the only feature to pattern. In the Transform toolbar, click the Rectangular Pattern tool. Use the Y-axis as the reference element. This can be done by right-clicking the input box, selecting Insert Wireframe and then choosing the Y-axis. Use the Instances and Spacing method with 4 instances and a spacing of 14 mm. Click Preview and check that the instances are created in the positive Y direction, if not, change the direction of the arrow. Click OK to create the pattern. In this step we will split the body by the offset surface, so that the depth of the tread will be the same as the offset value. In the Transform toolbar, click the Split command. Next, select the offset surface as the splitting element. Ensure that the arrow is pointing away from the origin, to keep the outer side of the geometry. Click OK to cut the geometry. In this step we will round off some of the edges using the Edge Fillet command. To help select the correct edges, we will hide the part body and the geometrical set containing the surfaces. To hide an item, right-click it and select the Hide Show option. We can now clearly see the edges. Next, in the Refine toolbar, click the Edge Fillet command. Set the radius to 2 mm. Now select the 7 edges of the rim which are shown. Click Preview to see the result. Click OK to create the edge fillets. In this step we will use a Boolean operation to remove the body from the part body. First, unhide the part body since we hid it in the last step. In the Structure toolbar, select the Remove command, found underneath the Assemble command. Select the body to remove as Remove Input. As you can see, the part body will then automatically be set for the From Input. Click OK to remove the body. Notice how the color of the body is kept, and therefore showing what was removed. In this step we will create 3 mirrors in order to form the complete geometry of the tire. Make sure that nothing is selected so that the complete body is mirrored. In the Transform toolbar, double-click the Mirror command to create several mirrors. First, we will mirror the tire to the front to create a quarter of the tire using the YZ plane as the mirroring element. Second, we will create the right half of the tire using the XY plane as the mirroring element. Finally, we will create the full tire using the ZX plane as the mirroring element. On the fourth mirror, click Cancel to end the command. As you can see, this was a more efficient way of creating the tire. We will now add a bit of detail to the side by adding the dimensions of the tire using a sketch and pad. Create a sketch using the flat surface on the side of the tire. Start with a circle, concentric with the origin. Make it a construction element. And constrain its diameter to 150 millimeters. Use the Text tool to create the text object. Type in the tire dimensions text. Change the font type, spacing and ratio to what is shown in the image. To align it correctly, click on the intersection point of the horizontal axis and the 150 mm circle. Clicking on the circle makes the text wrap around it. Adjust the alignment properties so that the text is on the outside of the circle and has the correct orientation. Check that the sketch is fully constrained. If not, it is possible that the point created for the origin of the text is not coincident with the horizontal axis or the circle. Create the constraints if necessary. Exit the sketch when you are done. Use the sketch to create a pad. Set the first limit dimension to 0.5 millimeters. Click OK to create the pad. We now have a nice text feature on the side of the tire. Due to the symmetric nature of the tire, we can rotate the text to copy it onto the other side. Select the text pad in the model tree. In the Transform toolbar, click the Circular Pattern tool underneath the Rectangular Pattern command. Use the Z-axis as the reference element. This can be done by right-clicking the input box, selecting Insert Wireframe, and then choosing the Z-axis. Change the parameters to Complete Crown and set the number of instances to 2. Click OK to create the pattern. The text is now rotated 180 degrees and is on the other side of the tire. In this step we will change the color of the part body to help distinguish it from the other parts in an assembly. Then we will add some materials and compute the weight. In the Tools toolbar, click the Object Properties command. Select the part body in the model tree. Then under Graphic Properties, change the color to match the displayed model. Next, we will use the Material Browser to apply the materials. This command brings up the search window. Use the Restore Down button and resize the window if necessary to see the model tree and geometry. In the search bar, type in name of the material to be used, in this case it is rubber. In the 6W tags, under Source, choose the public database as the collaborative space to search in. Find the rubber core material in the search results. Click the arrow on the right-hand side of the tile and then select Apply in the menu. Click on the part at the top of the model tree. In the contextual pop-up, ensure that the material is applied to the part. Then select the green check mark. Under Materials, you should now see the rubber material applied to the part. When you are finished, close the search window. Change the viewing mode to see the material. We will now compute the weight of the part. First, we need to activate the part product by double-clicking on the top of the model tree. Note that this will change the app to the assembly design. If not, use the compass to change the app to assembly design. In the Tools toolbar, click the BI Essentials command. In the pop-up window, select the weight definition from the drop-down menu. Click on the part and then select the second hyperlink in the pop-up to compute the weight. Click the Update command at the top of the weight table to refresh the values. As you can see, CATIA computes the inertia values for the part. Close the weight computation and the BI Essentials. Finally, reactivate the 3D shape to go back to the Part Design app.